Picture this, a universe just a few seconds old, a hot and turbulent cosmic soup of particles and antiparticles. Amidst this chaos, matter began to assert dominance over antimatter. Protons and neutrons began to take form. Yet, the formation of atomic nuclei, the recipe for creating elements, was blocked by an unexpected obstacle. This obstacle created a bottleneck, a cosmic traffic jam of sorts, where no further nuclear reactions could occur. The culprit? Deuterium. And just when all seemed lost, the universe cooled down enough for deuterium to stabilize. But here's where things started to get really interesting. But I'll just let you in on that in a moment. Hey there, Curiosity Explorers! Ready for another dive into the unknown? I'm your guide, Caesar, and with me is the insightful and ever-reflective Sonia.
Hello, fellow seekers of knowledge. I'm thrilled to join you all on this journey into the early corners of our universe.
Make sure you subscribe to Curiosity Wonderland, leave us a comment, and share our podcast with anyone who loves to take a deep dive into the wonders of the cosmos. We're all in this journey of discovery together.
Now, let's try to imagine what it was like when the very first elements formed. This is undoubtedly one of the most stellar accomplishments in human history. We have managed to decipher the intricate tale of our universe's birth, its evolution over time, and how it became what we see today. Just picture the early stages of the universe. It's a period we refer to as the Hot Big Bang. Everything was extremely dense, energetic, and rapidly expanding. At this point, there were no atoms, no atomic nuclei, not even protons and neutrons. Instead, we had a hot plasma of particles and antiparticles. As the universe expanded, it cooled down, leading to a series of pivotal changes. Matter started to dominate over antimatter. The electroweak symmetry broke, and the Higgs particle began bestowing mass to the universe. Protons and neutrons started to form, and the last vestiges of our cosmos's antimatter were annihilated. By the time the universe was just 3 seconds old, several key changes had occurred. There were no more free quarks, no more antimatter. Neutrinos ceased to interact with any remaining particles. We were left with a universe where there was more matter than antimatter, a billion photons for every proton or neutron, and a ratio of about 85% protons to 15% neutrons. And all this while the universe had cooled to just under 10 billion degrees Kelvin. But here's the interesting part. Although we had gone through all this cosmic evolution in just a few seconds, atomic nuclei, the determining factor in what element you are, could not yet form. It might seem simple enough to build elements in a universe filled with neutrons and protons. You begin by building deuterium, and everything else follows. But while it's easy to make deuterium, it's much harder not to destroy it. In the first 3 to 4 minutes after the Big Bang, the universe experienced a deuterium bottleneck. No further nuclear reactions could proceed until deuterium stably formed. As long as there were enough photons with sufficient energy to blast a deuterium nucleus apart, no heavy elements could form. Isn't it fascinating to realize what a crucial role deuterium played in the formation of the universe as we know it today? And believe me, we're just scratching the surface of this cosmic tale. Let's dive a little deeper. These early reactions all preserved a quantum property known as baryon number. The total number of protons and neutrons, as well as the electric charge, was conserved. At this point, when the universe was just a few microseconds old, we had an equal split between protons and neutrons, with precisely enough electrons to balance out the number of protons. But that equilibrium couldn't last due to a fascinating reason. The neutron is more massive than the proton. Following Einstein's equation E equals mc squared, it requires more energy to create a neutron and a neutrino from a proton and an electron than for the reverse reaction to occur. So, as the universe cooled down, more neutrons turned into protons than the other way around. At the end of the first 3 seconds since the start of the Hot Big Bang, the universe was 85 to 86% protons, balanced with an equal number of electrons, and just 14 to 15% neutrons. Picture this: protons, neutrons, and electrons all whirling around under unbelievably hot, dense conditions. It's like what happens in the heart of our sun, a real-life nuclear fusion reactor. It's easy to picture the process where protons and neutrons fuse together, building up heavier and heavier elements as they climb the periodic table and releasing energy via Einstein's E equals mc squared as these fusion reactions occur. Once you have atomic nuclei, you can envision a moment in time when the universe cooled enough to allow electrons to bind to those nuclei, producing all the stable, neutral elements we see in the periodic table today. It's mind-boggling, isn't it? I keep thinking about how astounding this universe of curiosities is. So many discoveries, so many incredible facts. The way our universe has evolved and transformed is just mesmerizing. What are your thoughts, listeners? Are you as blown away as I am? I'd love to hear from you. Don't forget to drop your thoughts in the comments, and if you're enjoying the content, do hit the like button. Let's continue this journey of discovery together. You know, this discussion brings to mind a recent event. Just the other day, I was observing the night sky, as I often do. Looking up at the stars, I was struck by the thought that the elements we see everywhere, not just in our sun, but in each and every star and galaxy ever discovered, had to come from somewhere. It's a thought that's worth dwelling on, isn't it?
That's interesting because I had a similar experience recently. As I was looking at a beautiful piece of jewelry, I found myself wondering about the journey of the gold, silver, and other elements in it. From being forged in the fiery cores of stars to ending up trapped in our planet's crust, then being mined, refined, and finally crafted into this piece of jewelry. It's quite a journey.
Exactly. It's easy to think that these elements might have formed from the start, right in the aftermath of the hot Big Bang. And that's a plausible pathway, but not the one that reality takes. Here's the strange part, those heavy elements do come from somewhere, but almost all of them are not from the Big Bang. Even George Gamow, the founder of the Big Bang theory, posited that this hot, dense crucible was the perfect spot to form these elements. But Gamow was mistaken. The universe does form elements during the hot Big Bang, but only a very select few. And the reason for this is something Gamow hadn't anticipated. You see, to make elements, you need enough energy to fuse them together. But in order to keep them around and build heavier things out of them, you must ensure you don't destroy them. And this is where the early universe, in the aftermath of the hot Big Bang, lets us down. In the early universe, it was easy for a free proton and a free neutron to form deuterium. But while energies were high enough, photons would come along and blast these deuterons apart, dissociating them back into individual protons and neutrons. So, to paint you a picture of what the early universe was like when it was only a few seconds old, we can say that it was filled with 85% protons, 15% neutrons, and about 1 to 2 billion photons for every proton or neutron. Isn't it amazing to think about how the universe we live in has gone through such extraordinary transformations? Our understanding of these processes continues to evolve, unveiling more and more of the universe's fascinating history. But for now, let's take a moment to marvel at the cosmic journey of the elements that make up our world. What are your thoughts? So, let's continue our cosmic journey. To create a heavy element, the first step involves colliding a proton with a neutron or another proton. The first step towards building anything more complicated out of the basic building blocks of atoms is to create a nucleus with two nucleons bound together. This might sound complex, but this part is surprisingly easy. The universe effortlessly makes deuterium nuclei. Proton-neutron collisions easily create the more stable deuterium and even give off a high-energy photon of about 2.2 megaelectron-volts of energy in the process. However, we face a problem here. The moment a deuterium nucleus is formed, it's promptly destroyed. This is where the story gets interesting. Consider this, in a hot, dense universe, where photons far outnumber protons and neutrons, the chances are high that as soon as you make a deuterium nucleus, the very next thing to collide with it will be a photon. And at the extraordinarily high energies found during the early stages of the hot Big Bang, those photons have more than enough energy to immediately blast that deuteron back apart into a proton and neutron. Now let's think about this. Even though a deuteron is less massive by about 2.2 megaelectron volts than an individual, free proton or neutron, there are a great number of photons present that are energetic enough to overcome that mass difference. And here comes the twist. Einstein's equation E equals mc squared, the very same equation that allows you to build up heavy elements through the process of nuclear fusion, can also prevent you from building what you want. Because for every reaction that occurs, the reverse reaction is also possible. So, this tells us that while the universe was creating elements during the hot Big Bang, it was also battling against its own laws that prevented it from keeping those elements around. Isn't it incredible to think about how the universe had to navigate its own complexities? Now, to understand the formation of heavier elements, we need to start with lighter ones, but they have to be stable. To give you an idea, of all the isotopes of the known elements, there are presently 251 known stable isotopes across 80 stable elements. However, these numbers may decrease with further research and better measurements. From the time that protons and neutrons are first formed, deuterium is continuously being created. But just as the universe can make it, it's also being destroyed at the same pace. Without that crucial first step towards creating heavier elements, we...
Sorry to interrupt, but I think it's fascinating how this process mirrors our own lives. We strive to create something, but often it's destroyed just as quickly. We face challenges that seem insurmountable, yet we persevere, we learn, we adapt, and we find ways to move forward, just like the universe did.
That's a profound observation. Indeed, the universe faced what cosmologists call the deuterium bottleneck. It's like a cosmic roadblock. It would love to build heavier elements, and it has the material to do so, but it must pass through an era where deuterium is so easily destroyed. So it waits. It waits for the universe to cool, which involves expanding, stretching the photon's wavelengths until they fall below the critical threshold needed to break deuterium nuclei apart. But this process takes more than 3 minutes. And in the meantime, the unbound neutrons start to decay. This means that only about 12% of the neutrons are left when the fusion starts. It's a dramatic race against time in the cosmic sense. To understand how this cosmic dance continues, we need to talk a bit about the concept of half-life. It's a term used to describe the timescale of radioactive decay. After one half-life, 50% of the original sample will have decayed away. After 2 half-lives, 75% decays away, and so on. Neutrons, like all particles, have a half-life that remains consistent throughout the universe's history. It doesn't change over time. Right now, a free neutron has a half-life of about 10.3 minutes. This means that if we wait long enough, every neutron will decay into a proton, an electron, and an anti-electron neutrino.
Can you give us an example to better understand this?
Absolutely. Let's think of it like a giant cosmic hourglass. Each grain of sand falling from the upper chamber to the lower one is like a neutron decaying. So in about 10.3 minutes, half of the grains of sand or neutrons would have fallen to the bottom. Now, if we wait another 10.3 minutes, half of the remaining grains of sand will have fallen. This process continues just like in the early universe where the proton-neutron ratio shifted over time. Now, after the universe had cooled enough, about 3.5 minutes after the start of the hot Big Bang, only about 12.4% of the original neutrons remained. But from this point, the real fun began, as we could not only build deuterium, but start to climb up the universal periodic table. Add another proton to a deuteron, and we get helium-3. Alternatively, add another neutron to a deuteron, and we get hydrogen-3, better known as tritium. From this point on, we see that elements beyond helium-4 are very difficult to create. By the time the universe is 3 minutes and 45 seconds old, practically all of the neutrons have been used to form helium-4. Now what we end up with if we measure the various elements by mass are about 75.2% hydrogen, 24.8% helium-4, a tiny fraction of deuterium, tritium, and helium-3, and an even tinier trace of lithium-7 and beryllium-7. Unfortunately, that's the end of the line for nuclear fusion during the hot Big Bang. The universe has expanded and cooled enough to make its density tiny, only 1/billionth the density found in the sun's core.
You know, this talk of elements and their creation reminds me of a childhood memory. My father was a jeweler by trade. I remember as a child seeing him melt down old pieces of gold jewelry, then skillfully crafting that into something new, something beautiful. It was like magic to me then, but I guess in a way it was not too dissimilar from what we're talking about. Just as my father restructured basic elements into beautiful jewelry, the universe, in its initial moments, was restructuring its basic elements to form the complexities of the world we know today.
That's an illuminating memory and a great analogy. As we've discussed, the universe had to go through many processes to make the elements we have today, much like the jeweler who takes raw materials and with time, heat, and skill creates something new and valuable. However, Unlike the jeweler, the universe's creative process ceases at lithium, at least during the hot Big Bang. From there on, the creation of heavier elements requires different conditions. Much like a jeweler needs different tools and techniques to work with different types of metals and gems. So, the universe commences the grand creation of elements right after the Big Bang. But it's fascinating to note that what it cooks up is almost all hydrogen or helium. There's only a tiny crumb of lithium left from the Big Bang, about 1 part in a billion by mass. And once the universe has cooled down enough that electrons can bind to these nuclei, we have our very first elements, the primal building blocks that the first generations of stars will be made from. But here's the kicker. They're not made up of the elements that we consider vital to existence, like carbon, nitrogen, oxygen, silicon, and phosphorus. No, it's almost entirely hydrogen and helium, to the 99.9 repeating percent level. So the cosmic journey that leads to us, to all the complexities and wonders we see around us, it all begins in less than 4 minutes from the start of the hot Big Bang. That's all it took to go from nothingness to the first stable atomic nuclei, all happening in an ocean of hot, dense radiation that was constantly expanding and cooling. That, dear listeners, is the story of our universe's humble beginnings. The cosmic story that leads to us, to you, to me, has finally begun. So we've journeyed to the dawn of the universe, to the hot Big Bang. A time before atoms, when there was only a plasma of particles and antiparticles. As the universe expanded and cooled, a cosmic dance began. Matter won over antimatter, and protons and neutrons were born. Deuterium was the key, but the early universe was just too hot for it to stick around, creating what we now call a deuterium bottleneck.
But patience is a virtue, even for the universe.
Indeed, after a few precious seconds, the universe cooled enough. Deuterium was here to stay, and nuclear fusion truly kicked off, crafting helium-3, tritium, and with even more protons and neutrons, the very stable helium-4.
But not everything that glitters is gold. The universe's density by this point was too low for further fusion, so the elements beyond helium-4 were just off the table.
Quite right. The universe gave us plenty of hydrogen and helium, a dash of lithium, and left the rest of the periodic table for another story. All of this unfolded in less than 4 minutes from the Big Bang. If that's not a cosmic speedrun, I don't know what is.
And that, dear listeners, is the incredible story of our humble beginnings, written in the stars, penned by the universal forces at play. It's been an absolute pleasure to walk you through this cosmic journey. Remember, if you loved this episode, don't forget to blast that like button, drop us a comment, and share this cosmic mystery with your friends.
So, until next time, keep gazing at the stars, keep asking questions, and remember, we are all stardust, forged in the furnace of the hot Big Bang. Sonia and Cesar, goodbye. This cosmic journey was inspired by What Was It Like When the First Elements Formed, written by Ethan Siegel and published on Big Think on November 30th, 2023. You can find the full URL in the video description if you want to dive deeper into the subject. Now, I'm off.